Today we are going to discuss adiabatic mode in some detail because it's there. And the first question is, how do you formulate initial conditions for the adiabatic mode? As we discussed, adiabatic mode, let me remind you, is the mode in which everything is the same in different places in the universe, except maybe for energy or overall energy density. Energy density is different in different places in the universe. The gravitational potentials, therefore, are also different, but chemical composition is the same. So this is one and the same universe. The different patches in the universe, which are widely separated. So we are talking about super-horizon physics, the physics at super-horizon scales. So different parts of the universe which are separated by distance much bigger than the Hubble distance, they look the same, except they may be, in a given gauge, they may be at different stages of their evolution, effectively, right? So what could be the difference between two patches in the universe in which the composition of matter is the same? This is the beginning, the initial Big Bang. When do they start? So effectively, they look like they have started at different places at different times, and therefore they evolved in somewhat different periods of time, and therefore in some place the energy density has diluted more, whereas in the other place it has diluted less, right? So we're going to exploit this concept of independent quote-unquote universes, which is actually a very fruitful concept technically. Different universes, quote-unquote, different patches in the universe, which are all the same, except they have been evolved a little bit in during different times. We will explore this to figure out precisely what the conserved quantity is. What is the quantity which is truly independent of time in the superhorizon regime? We were talking that we have seen that, for example, gravitational potentials in conformal Newtonian gauge stay constant in time, or density contrasts also stay constant in time independent. But this is not always true. What we need is actually precise conserved quantity, conservation law, if you like, in the superhorizon regime. Why do we need that? We need that because our universe passed through different stages. We know of radiation-dominated stage, we know a matter-dominated stage, in the past possibly inflationary stage. So we want to know how the universe proceeded through the transition periods between these stages, what was conserved, what quantity was conserved during this transition, okay? So that we calculate, we'll calculate this quantity in inflationary scenario, in inflationary model, go well outside the horizon, okay? And this quantity will be conserved, whatever happens afterwards. Whatever reheating process, very turbulent probably, after inflation, how the universe got into the radiation domination epoch, etc. They are all pretty complicated processes, but once you consider the wavelengths much bigger than the horizon size at all these processes, at all these times, then this quantity will be conserved. So we will not need to follow its evolution. Since it is conserved, it's just a constant through the entire evolution, okay? That's the whole point. That quantity is called Zeta, and it characterizes completely adiabatic mode outside the horizon. So, so let me introduce what it is. Right, so we are talking, again, let's think of the different patches of the universe which have experienced somewhat different periods of evolution, okay? What does it mean? This means that if I have, let me label by lambda, the various types of matter, dark matter, radiation, or whatever matter have you, okay? So what is in formulas saying that my my universe is the same everywhere except that some regions advance, some region lag behind the average evolution. This means simply that the variation of density of each species, each types of matter, is proportional to time derivative of the energy density times this mismatch in times, which I call epsilon, which depends on x and eta. Okay? This is mismatch between the time, the duration of the evolution at point x with respect to average evolution. Okay? Likewise, delta p lambda must be the same story, right? This is epsilon, same epsilon times p lambda for all types of matter. And also, since I'm doing the adiabatic mode, the motion of all types of matter is coherent. They move with the same velocity. So v lambda v, and this is independent of lambda of matter. So if there is motion, then the matter moves as a whole. So dark matter moves in the same way as baryon photon component. The entire motion is all the same. Okay. So epsilon is the only parameter, is the only function at this point common to all forms of matter, right? And it says, okay. So, so the idea now is to consider superhorizon regime, meaning that I sent my momenta to infinity. Oh, sorry, to zero. To zero. The time, the derivatives, the spatial derivatives are negligible since we are considering very long wavelength perturbations. And well, I'm talking about the scalar perturbations, of course. So there is no, what I'm saying refers to scalar perturbations, of course. So now we want to use these equations, which are again the same equations I showed you yesterday, to figure out what is the time-independent quantity. What is the integral of motion? To this end, let me remind you that these equations here are valid for each lambda. These are covariant conservation equations valid for each type of matter if this if the matter if it decoupled from other forms of matter. Now, let me use the conservation equation, the first conservation equation. Let me write it down here. Delta rho lambda prime. Let me put here our expression with epsilon. So this is epsilon 3a prime over a epsilon p lambda prime plus rho lambda prime, right? Now the gradient, the Laplacian of velocity is negligible. I sent my momentum equal to 0. So there remains one more term, which is p lambda plus rho lambda times 3 psi prime. Okay? That's my equation number 5 on this slide. Okay? With this specification. Right, now I use the fact that I use again this identification that delta lambda is this thing here. I differentiate it. So this term here becomes epsilon prime times rho lambda prime. Now let's see. Let me write this way. So this delta rho prime is epsilon rho prime. Rho prime is minus 3 a prime over a rho plus p, right? Everything prime. Okay? That's the use of our covariant conservation of the background draw. Right? Ground draw obeys rho prime is minus 3 a prime over a p lambda plus rho lambda. That's true for any type of matter. This is background, the covariant energy conservation for background. Okay? And then I write this as minus 3 epsilon a prime over a prime p lambda plus rho lambda, and the rest is minus 3 epsilon a prime over a p lambda prime plus rho lambda prime. Okay? This is the first term here. We see that this term and this one cancel out. The overall factor here and here is the same. So I get a suggestive equation that psi prime equals to epsilon a prime over a prime. Okay? Which means that my psi equals to epsilon a prime over a plus zeta. And this is precisely conserved quantity. Zeta is independent of time. Zeta depends on x only. Right? So I've got conservation equation. Conservation equation for the quantity zeta of x, which is equal to psi minus this thing here. But this thing here, epsilon is delta rho divided by rho prime, and I can use this rho prime to cast this into the form which is now independent of the introduced epsilon. This is delta rho divided by 3 times phi plus rho. And I can either put lambda here, or I better put total, because this is true for everybody. So I could take a sum of the left-hand side and the right-hand side and write down the same thing for total energy density. Okay? So this is my zeta. This is conserved quantity, and this is full generality, right? I didn't use anything but the conservation equations, and definition, essentially, of the adiabatic mode. This can be viewed as a definition of the adiabatic mode, right? Very good. So this is the constant throughout the whole evolution of the universe, provided that my permutation is superhorizon. Okay? And this zeta determines everything else for superhorizon adiabatic mode. It's not, I mean, for example, what is the velocity in the, no, let's see, not velocity, let me just, well, actually, now I cannot be that generic, because you see there are two potentials, phi and psi, okay, and the relationship between the two involves has to do with this equation here, which which contains k squared here. So this tells you, by the way, that this pi, the anisotropic stress, is suppressed as like k square in superhorizon regime. That's good, because you can neglect it if you work to the zeroth order in momentum. But that's bad, because the relation between psi and phi comes from this equation, which is k squared equation, right? And there are all kinds of subtleties if you want to relate phi and psi, and without this relation you can't close this system. And in particular, this subtlety shows up when you consider neutrino contribution, neutrino fraction. Neutrinos are not ideal fluid. There is non-trivial anisotropic stress pi for neutrinos at the level of k squared. So for neutrinos, this is a non-trivial relation. Okay. But if you consider perfect fluid, then everything is simpler. And let me do that. Suppose we are dealing with ideal fluids. For an ideal fluid, as we know, for ideal fluid, okay, I should probably leave that psi prime equals a prime over a times epsilon prime. For ideal fluid, we know that psi equals to phi minus phi. Okay, that follows from equation number 4 here. This is a trivial equation even at the level of k squared, if pi is 0, if we are dealing with ideal fluid. And then we can plug this in here and obtain equation for epsilon, for example, right? Because, and zeta, which expresses epsilon in terms of zeta. And epsilon is, after expressing epsilon, we know everything. So this equation, the first equation here, again we neglect this term with Laplacian, we get simple equation 3a prime over a psi prime plus 3a prime squared over a squared psi equals 4 pi g a squared, and then delta rho is epsilon rho prime total. Okay? And this is equation for epsilon because we know that psi is a prime over a times epsilon plus zeta. Okay? So this equation expresses this function epsilon that enters here and here. It expresses it gives you an equation for this epsilon, and it's straightforward to work this equation out. You just plug psi in this form here. Remember that zeta depends on coordinates and use the background equations of motion. Anyhow, what you get is that epsilon prime plus 2a prime over a epsilon plus zeta equals 0. Okay? Right. So, and in this you write that rho total is related to the a, like this, 8 pi over 3 g equals a prime square over a to the fourth. This is our Friedman equation in conformal time. You differentiate this, plug this in here, do algebra, and get this equation here. So epsilon is expressed in terms of zeta. Remember, this is function of x, and all the rest is known, provided you know the evolution of your background. A squared integral from 0 to eta d eta prime a squared of eta prime. Okay? So once we know the initial condition zeta, and we know the evolution, at which stage of the evolution we immediately calculate epsilon. Why the lower limit of integration is 0 is this is true for radiation method domination. Otherwise, this epsilon will be divergent because a goes to 0 as eta goes to 0. So I don't want this epsilon to be divergent in the past, and therefore my limit of integration is 0 for radiation method domination. Okay? Very good. So together with this equation here, this solution gives me the gravitational potential. If I am in the ideal fluid approximation, then my phi is equal to minus psi, and then my energy densities, pressures, are expressed through this function epsilon. So I'm done. I know everything outside the horizon for the superhorizon mode, and let me also figure out what the velocity is. Velocity potential. It is also straightforward. My velocity potential is here. It's all the same for all types of matter. So you can plug this out here. And then if phi and psi are the same, you neglect this term here. If phi is equal to minus psi, then obviously the left-hand side here and here are the same modulo factor of 3a prime over a. Okay, so you do a simple algebra, subtract one equation from another with appropriate factor of 3a prime over a, and you get from these two equations, you get an equation that involves only v, which is minus 3 p plus rho total a prime over a times v equals to delta rho, but delta rho is epsilon rho prime, epsilon rho total prime. Okay? And lo and behold, this term is also equal to rho total prime. So V is simply equal to epsilon. So the meaning of this parameter epsilon here is just the velocity of the medium in the case of perfect fluid. Actually, this is not even for perfect fluid. This is true for any type of matter filling the universe. So this parameter epsilon has meaning of velocity. Okay, so let's maybe give a couple of an example of using this. We will use this repeatedly when we discuss generation of perturbations at inflation. What we are going to do is to calculate this zeta in inflationary context, for example. All right? Once you calculate this zeta at generated at inflation, once you get your modes behind the horizon, then this zeta is a constant, and what you calculate at inflationary epoch is valid even late at the radiation domination, but before the horizon entry. So you cross huge span of time in logarithmic scale without doing anything, just having a conserved quantity through the whole evolution of the universe. That's the strength of this approach. Okay, so let's apply this. How do the parameters, how does this work for radiation domination? For radiation domination, A is proportional to eta. Okay? And epsilon is equal to minus 1/3 of eta times eta. You do this integral. A is linear, 1/3 therefore. Okay. Then gravitational potential psi equals minus phi equals A prime over A, 1 over eta epsilon plus zeta, which is 2/3 of zeta. Delta rho, say what I will need. Okay, the delta rho radiation, okay, as an example. What it is? It's epsilon times rho prime, which is minus 3 A prime over A is 1 over eta, and 1 plus 1/3 rho radiation. Okay, this is P rho plus P radiation. So altogether it gives me minus 4/3 of zeta. Okay, am I right? 4 times 2 over 3. Oh. Am I right? Is it 8 over 3 or 4 over 3? Ah, no. Epsilon is 1/3. Okay, good. So, right. So this is minus 4/3. Epsilon is, yeah. All right. So that's you can calculate the same for times rho radiation. So delta radiation is minus 4/3 of zeta. Okay, etc. And if you have non-relativistic matter, for non-relativistic matter here I will have just 1. So delta meta will be equal to minus zeta. Okay. Sign here is wrong because here I have minus, here I have another minus, so altogether this is plus. Okay, so once I know this function zeta, then in the superhorizon regime I can calculate everything, the gravitational potentials, delta, the density contrast from radiation and matter. They're all constants, and they're all related by numerical factors which depend on the evolution epoch. These numerical factors depend on the epoch of evolution, but they are all related to this zeta. And as a first use of it, example of using this eta, let's do the same thing for matter radiation. So this is radiation domination. For matter domination. For matter domination, my A is eta squared, right? So here I get 1/5, right? Because here I have eta to the 4th, I integrate, get 1/5. So epsilon is minus 1/5 zeta times eta, right? So psi is A prime over A is 2 over eta epsilon plus zeta equals 3 over 5 of zeta. You see, that's the example of how you cross without doing anything, how you cross from radiation to matter domination. Gravitational potentials change, right, by a factor of 9 over 10, right? This is the gravitational potential at radiation domination. This is gravitational potential at matter domination. So without doing any calculation, any dynamical calculation, you figure out how these gravitational potentials change once you pass from one epoch to another. Okay? Or the value of delta rho radiation, in this case, it is again epsilon minus 3 A prime over A is 2 over eta. Okay, this is, I use repeatedly this equation here. First third of rho radiation. It's again the same calculation, but with A prime over A different and epsilon different. So all in all, I get 8 over 5 rho radiation. Or delta radiation is 8 over 5 zeta. Okay? So you see, this zeta is a constant, but once you pass from radiation to matter domination, numerically, the density contrast in radiation, for example, changes from 4 over 3 to 8 over 5. Okay? And this is not innocent. You may think, well, this is numbers. Who cares? Well, you care because cosmic microwave background knows about all these stupid numbers. It does show you that you, by one and the same function zeta, which is, I will discuss what it is, but by one and the same function, you describe the whole set of CMB data, and of course, some perturbations are still superhorizon by the recombination, and they are recombination occurs at matter domination. So for these very long wavelength perturbations, this is the right expressions for gravitational potentials and density contrast of photons and baryons by recombination. Okay. Whereas for others, they are no longer superhorizon by recombination, shorter wavelengths. And for shorter wavelengths, the correct initial conditions for their evolution, if they enter the horizon radiation domination, the correct initial conditions are given by this formula. Okay, so all these numbers are directly measurable. Right? Very good. Now, does this zeta has any physical significance? How can one interpret it? What is its meaning? Does it have any meaning? The answer is yes. It has a nice meaning. And let me discuss this meaning. Let's consider, okay, we are in the conformal Newtonian gauge. By the way, all this discussion can be done in arbitrary gauge, not necessarily conformal Newtonian, but then you have to, introduce more, work harder a little bit. But we are in conformal Newtonian gauge, and what I'm going to do now is to do gauge transformation, which eliminates delta rho. Okay? Gauge transformation in general relativity is just the coordinate transformation. So what I'm going to do is to go to slices of space-time on which energy density stays constant, is independent of space. Okay? So in conformal Newtonian gauge, my delta rho is non-zero, but I can choose slicing in such a way that everywhere on a given spatial slice, energy density is the same. Okay, so delta rho is 0. For that, I need the gauge transformation. I wrote the gauge transformation for G mu nu for metric tensor, but I could do the same thing for energy momentum tensor. The difference is that my energy momentum tensor has one upper index and one lower index, and therefore its gauge transformation is a little different. T mu nu tilde at x, this is the gauge transformation if you do the same gauge transformation as in the case of, as I did with metric. Then the gauge transformation of energy momentum tensor will be this, plus minus lambda nu. This is not quite the same as for the metric tensor because my index mu here is an upper index. And here it's the same as in the metric tensor for index mu, psi lambda, t lambda mu, and the usual story, d lambda t mu nu psi lambda. That's the general gauge transformation, infinitesimal gauge transformation, but energy momentum tensor. And let me remind you that gauge transformation of G mu nu tilde of x is similar, is G mu nu plus d mu psi lambda G lambda nu plus d nu psi lambda G lambda mu plus d lambda G mu nu psi lambda. Okay. So these two look familiar because they act on the same type of index, on the lower index nu, whereas here I have a difference between my index mu here is upper index. Anyway, under this gauge transformation, you plug your expression for T mu nu in here, and obtain that delta rho tilde, the new density perturbation, it actually comes from the last term here. These two cancel each other for T naught. Delta rho is delta rho plus rho prime psi naught. So I can cancel this delta rho out by choosing suitably psi naught, by choosing it equal to delta rho divided by rho prime. Okay? Now, from the gauge transformation here, let me calculate what is delta Hij. Delta Hij, well, it will receive contribution proportional to second derivative, but what's important for me is that delta Hij tilde is delta Hij minus 2a prime, minus because, okay, G mu is proportional to AT mu, minus 2a prime over a delta Ij psi naught plus terms which involve psi I. But let me do the gauge transformation involving only psi naught. Then this is the right expression. Okay, so I don't do the transformation of spatial coordinates, only time coordinate. Okay, so this means if I recall what the Hij was equal to minus 2 psi delta j. This gauge transformation means that psi tilde equals psi plus a prime over a times psi naught. Okay, and here is my psi naught. So what I get is psi minus a prime over a delta rho divided by rho prime. Rho is total energy density. I just skip the subscript total. Okay, so I take the total energy density to be homogeneous over the entire space. In this frame, I get new gravitational potential, and now I again recall that rho prime obeys this equation here. Okay, and I immediately recognize that this is precisely zeta. So zeta means metric in, so the dl squared, the spatial metric is a squared times 1 plus 2 zeta delta ij dxi dxj. So zeta means the diagonal part of the metric in the frame where matter is homogeneous. So I can make the coordinate choice such that the matter remains homogeneous, the energy density stays constant, but there are perturbations in the metric, and behind the horizon this is precisely this zeta. if I calculate the spatial curvature, the Riemann scalar, the scalar curvature of this three-dimensional associated with this three-dimensional metric, then I get modular number. I don't quite remember what it is, but it's like -4, I think, Laplacian of this zeta. So this zeta is sometimes called curvature of how is it called? Curvature of hypersurface where matter is homogeneous. Okay, on which matter is homogeneous. Another interpretation, -4 over a squared. That's the right answer. Another interpretation is the following. We know that epsilon is the same thing as velocity. Therefore, my zeta is equal to psi plus a prime over a times velocity. Right? Velocity potential. Okay? So I can do the same trick. I can ask what is the metric on the hypersurfaces on which velocity is 0. Okay? Velocity characterizes a component of energy momentum tensor, mixed component, 0I component of energy momentum tensor. So velocity potential transforms, and in fact it transforms in a simple fashion. V transforms to V plus psi naught. You can use this formula for energy momentum tensor, plug in the components of energy momentum tensor we had, and figure out that this is the transformation law for velocity. So if you do the same, am I right? Yeah, possibly with minus sign, but never mind. So, so if I do gauge transformation to the frame where velocity is 0, then I will figure out that zeta is actually equal to psi tilde at V equals 0 hypersurfaces. So another interpretation of this parameter is that it's a metric or spatial curvature it's a metric on the comoving hypersurfaces. Hypersurfaces on which the matter doesn't move. That's actually quite convenient because comoving hypersurfaces, the surfaces on which the matter stays constant, I mean, it doesn't move, they are easily generalized to theory of scalar field, to inflation. There, identifying velocity is relatively straightforward with the derivative of the field, and therefore you more easily understand what the expression for zeta is in the theory of the universe governed by the scalar field, inflation. Okay, so the two interpretations are zeta is the metric on the 1 plus 2 zeta delta ij, gamma ij, plus 2 zeta delta ij times a squared is metric either on hypersurfaces of constant density, constant energy density, or this is the same thing as metric on hypersurfaces of on comoving hypersurfaces with vanishing velocity. Okay. So why did I spend so much time on this zeta? Because if you look at the papers where data are analyzed, then basically the part which analyzes, which gives answers for the initial conditions, it gives answers for this parameter, this function zeta. How does it behave? Okay. This brings me to the next topic, what actually is known about this zeta. Okay. Well, there is wealth of data, and known is a lot. Mostly from cosmic microwave background, but not only. There are other data which are complementary, which give you additional information. So we know quite a bit about this. So this brings me to the topic of summary of experimental results. So we're talking about adiabatic perturbations. And in the first place, zeta of x is a Gaussian random field. What does it mean? What does it mean? What does it mean, gentlemen and ladies? Right, yeah. Now, this means that the correlation functions obey weak theorem. Okay, do you know what is weak theorem? Hope you do, right? Zeta of x, zeta of y, x1, x2. x4 equals the product of 2-point functions. Zeta of x1, say zeta of x3 times zeta of x2, zeta of x4 plus permutations, plus 2 permutations. Okay? This is Wick's theorem for particle theorists. For in other words, the probability distribution is determined by integral with the weight e to the minus 1/2 zeta of x d minus 1 x y zeta of y. Okay, integrated over dx dy. So if you want to calculate correlators, and this guy depends on coordinates only, so this is 3-dimensional integrals here. If one wants to calculate correlators, then one calculates the path integral with this weight, okay, with this exponential weight, where d is just this dxy is this correlator, x zeta y. That's why it's called Gaussian. I actually don't quite know why is it called Gaussian. Is it because Gauss invented this measure, or because this quadratic e to the square divided by 2 is a well, anyway. So we, I mean, there's a Gaussian measure here, okay, and it follows from this Gaussian measure that the correlation functions obey Wick theorem. This is, by the way, very suggestive for us particle theorists, because what are the 2-point functions or correlation functions that obey Wick's theorem? We know a very nice example of that, and probably the only example in particle physics. These are correlation functions of free fields in vacua, right? We'll start our, this myself, our education in quantum field theory by studying free fields and figuring out that the correlation functions of free fields obey Wick theorem, right? Free fields in vacua only, in the vacuum state. So this tells us essentially that probably the origin of the density perturbations is vacuum fluctuations of free fields, which evolve linearly. Linearly means there is no interaction between modes. So there are parametric enhancement, there should be parametric enhancement of these vacuum perturbations, but the equation for perturbations, equation for the fields should remain linear, and then Wick theorem will persist. Okay, so this is Gaussian random field, and all attempts to find non-Gaussian features, deviations from the Wick theorem, were not successful. There are strong, actually pretty strong, bounds on non-Gaussianities from Planck. So it is a Gaussian random field for the time being. Now, not only it is Gaussian random, but it's also homogeneous and isotropic. What does it mean for random field? For random field, this means that its correlation function, the only correlation function relevant, is actually a function of the distance between the points x and y. All right? It doesn't know about directionality between these 2 points. It doesn't know where they are. It's a function of modulus of x minus y. Okay? Or if you write it in the momentum representation, let me introduce psi of x in the momentum representation is dk d3k e to the ikx zeta of k. I wrote this for normalization, to show normalization I'm going to use. Correlation function of zeta of k, zeta of k prime must be, due to translation invariance, it must be proportional to delta k plus k prime. Okay, in these notations, then indeed my function will be function of a difference between x and y in coordinate space. And it should be, the coefficient here must be function of modulus of momentum only. This is rotational invariance. 4 pi k cube p pi zeta of k. This is a handwritten p. Oops. This is a handwritten p zeta of k. It depends on the modulus of k. Again, this is an issue of experiment. I mean, we don't know offhand whether our Gaussian field is actually isotropic. I mean, at the time when it was generated, the universe could have been anisotropic, and then this will give you the this function p, the 2-point function, which depends on the directionality of momentum. Right? If the universe was anisotropic, then the modes of momentum of different directions of momentum could be generated in different fashion and have different strengths. And there are models of this sort. Again, there are pretty strong constraints on what is called statistical anisotropy, dependence of this P on directionality. Okay, so this is isotropy is a question, and it is true that at a given at present level of measurements, this Gaussian random field is indeed isotropic. Homogeneity, I'm not sure if anybody has looked at it. It occurred to me whether indeed you have this property of delta function. Probably so. Anyhow, normalization here is chosen in, that's a standard normalization. It is chosen in such a way that if you calculate the fluctuation that zeta square of x at a given point, then you plug this in here, you take the square of this, plug it in here, use the delta function, this will become d3k over 4 pi k cube p zeta of k, which means that I go to one-dimensional integral over modulus of momentum. This will be simply integral dk over k from 0 to infinity to indicate that it's a modulus p zeta of k. Okay? That's the reason for normalization, so that this p zeta of k tells you how much every decimal interval or logarithmic interval of momenta, how much does it contribute to the fluctuations of your variable. Of course, nobody measures this fluctuation at a given point. You always smear it with a certain smearing function, but that's convenient to understand the meaning of this p of zeta. This is the contribution of the logarithmic interval of momenta to the fluctuation. Okay. Now it's standard to parameterize this p zeta sometimes there are experimentalists like, not only theorists but also experimentalists like to use fancy notations. So some people use notation PS. Some people use notation delta squared zeta or delta squared S. And sometimes they even have different notation, PR and delta R squared. So if you look at different, say WMAP uses, I believe, this one, maybe that one, delta, the last W. The previous WMAP used PR, etc. So I mean, the Planck uses PS, okay, for scalar. But they are all, this is one and the same quantity. Okay, anyhow, the standard parameterization for it is that it's power law. It's an amplitude times k over k star power ns minus 1. P of k, where A is obviously the power. This P is called power spectrum, and A is the amplitude. It's the value of the power spectrum at a given momentum k star, and K star is a matter of choice. Again, different experimental teams use different value for K star. Planck uses 0.05. That really doesn't quite matter for us. 0.05 megaparsec minus 1. This is with a not equal to 1. So this is just the momentum or wave vector in the present universe. This particular wave vector. Okay? Right, so the simplest parameterization is this one. And it is motivated by two things. One is that in the beginning of 70s, can you imagine? Cosmologists suggested that this power spectrum should be independent of momentum at all. These were Harrison, Zeldovich, and Peebles and Yu. There were 3 papers, which independently suggested that this power spectrum should be independent of momentum. Then ns equals 1. This is historical. Ns equals to ns minus 1 as a power. For ns equal to 1, this is Harrison, Zeldovich, Peebles, Yu suggestion, guess, and they were correct to a very good approximation. But not quite. Another motivation is that in inflationary theories, with a simple slow roll inflation, this scalar spectral index ns is indeed close to 1, and the dependence on momentum is pretty mild and is well parameterized in this fashion. Okay, so there's nothing beyond that. Sometimes, of course, you may be more sophisticated, and people discuss also ns that depend on k, which is ns at k star plus dns for d logarithm k at k star times logarithm k over k star, and call this term, this parameter here, scalar spectral index, dns over d logarithm k. Running index. This is called running. This is scalar spectral index. This is running index. So, so what's known about that? It's known that the amplitude a zeta, well, it's slightly varies within roughly to sigma. It's 2.20 plus or minus 0.06 times 10 to the minus 9, according to Planck, and 2.43 plus or minus 0.08 times 10 to the minus 9, according to WMAP. So it's in the ballpark of 2.5 to 2.5 times 10 to the minus 9. This is square of the amplitude. Okay? And that's why this notation here. It's square of the amplitude, it's square of zeta, right? So it characterizes square of the amplitude of your perturbation. So my perturbation is indeed at the level of 10 to the minus 4 to 10 to the minus 5, right? Square root of this 8 zeta is a characteristic perturbation of my density perturbations, okay? Initial value for it. Okay, the ns, already WMAP, claimed that it is not equal to 1. And the W map says that it's 0.97 plus or minus 0.01, and Planck 0.96 plus or minus 0.07. So this is Planck. They are consistent with each other. And this is W map. So very good. We have slightly red spectrum of pretty small amplitude, 10 to the minus 4, even somewhat less. If you want to see what are the limits on the running index, you can go to papers and take a look. They give limits on the running. Running isn't observed. This DNS over D logarithm k is consistent with 0. So that's basically it for adiabatic perturbations. But as we discussed, there are also possibly tensor modes. And tensor modes also, let me introduce the notations. It is expected, if you believe in inflationary theory, it is expected that gravitational waves, tensor perturbations, are also Gaussian random fields. Needless to say, homogeneous and isotropic. And they have their own power spectrum. So the polarization modes, coefficients of polarizations, remember we introduced them in our lectures. They obey delta alpha beta because of isotropy, and the same story, 4 pi k cube p tensor now of k delta k plus k prime. So that the perturbation hij squared, hij at given point x, there are two polarizations, hence this factor 1/2 is equal to dk over k p tensor. Okay, so how you characterize the presence or absence of tensor perturbations? You define R. This is fortunately one and the same letter used by everybody. R ratio, which is ratio of tensor to scalar at k star. Tensor power spectrum to scalar power spectrum k star. And today we have Planck limit 0.11 for this R at 95% confidence level. So let me show you figure. Here it is. Oops, no. Before bicep. Here it is. This is the Planck data of 2013. This is the scalar spectral index. This is the Harrison-Zeldovich-Peebles-U point, 1. And this is the 1 sigma confidence level, 2 sigma confidence level contours. Planck used also the data on small angular scales obtained by WMAP. Polarization obtained by WMAP, and also data on baryon acoustic oscillation. I will tell you what they are in a second. Okay, so that's the picture. You see the 0.11 is somewhere here. That's the bound from Planck, and all these straight lines are inflationary predictions. This intervals are inflationary predictions for different inflationary models. We'll discuss that later. So some models have been ruled out. Phi to the fourth inflation, by the way, is way up here. Phi squared is here. It's on the wedge of being ruled out. So the inflationary potentials that were considered most plausible are now less plausible from the viewpoint of the observational data. By the way, let me just show you the story about BICEP. The BICEP claim was that R is equal to 0.2. And this is large. It's actually about 10% contribution of temperature fluctuation at low multiples. It's a large contribution. So if the BICEP wants the R ratio to be somewhere in here and the scale spectrum index somewhere in here, whereas on the same scale the previous picture is this. So it's clear that there was already at the moment when the BICEP result was released, it was clear that there was a tension between existing WMAP, existing Planck data and BICEP, and now it's it's quite plausible that BICEP was overestimating signal if they had any signal at all. Anyhow, so that's the summary of experimental data. And let me give you now let me summarize what we have done so far about the adiabatic mode. Since I'm heading towards the discussion of cosmic microwave background and isotropies, it would be important for me to understand what we have for adiabatic mode at the epoch of photon loss scattering. Okay? So to summarize, I did not right, okay, so summary at recombination. So at recombination, or photon loss scattering, which is the same thing for me. What is the adiabatic mode at recombination? Well, for superhorizon modes, K eta recombination much less than 1, superhorizon at recombination, and we know that the corresponding angular scale is about 2 degrees. We know that the potential phi is equal to minus 3/5 zeta delta in radiation in baryons and gamma, which by recombination travel together. It's 8/5 zeta, which I just calculated. I didn't calculate velocity. Velocity, VI, is suppressed. It's IK, IV, where V is velocity potential. And we have seen that velocity potential is proportional to eta, so it's minus I/5 KI. This I did not, well, actually I did, because I calculated epsilon. At matter domination, this is 1/5 is just the coefficient that I had for epsilon times zeta. Okay? So velocity is suppressed by this factor here at a recombination. At recombination epoch, that's what I need. I need the gravitational potentials, I need the density contrast, and therefore temperature contrast, and velocity of my medium. Okay? For subhorizon modes at recombination, situation is different. Subhorizon modes. And let me summarize the modes that enter the horizon at radiation domination epoch, because at the transition between radiation domination and matter domination, it's more difficult to get analytical understanding of what's going on. But for sub-horizon modes which are short, such that k at equilibrium is less than 1, they enter the horizon at the radiation dominated epoch. We know that there are acoustic oscillations, and we calculated it, and it's translated into zeta. This will give us 4 minus 4 zeta times cosine of the radius of distance of sound. Is that, yeah, times k. And this is coordinate distance to sound horizon. Rs equals to be more accurate, it's equal to V sound, U sound, d eta. That's right. From 0 to combination. This is the. In fact, this velocity of sound slightly depends on time, because we have not only photons but also baryons, not only relativistic particles but also non-relativistic particles in the baryon photon medium, and therefore pressure is not quite equal to 1/3 of energy density for this medium because of baryons, and therefore the sound speed is not quite equal to 1 over square root of 3. So that's more accurate, and that you can easily figure out if you know what is the portion of baryons in your system, and we know what it was. Okay, well, that's not the only part. There is another part, and it has to do with potentials. Why is that important? Because the photons that come out from potential wells, they are more red as compared to photons that come from potential hills. This delta, the relative energy contrast in energy density, is the contrast in temperature as well, right? So that's also important for CMB photons. Velocity, which I will not talk much about, is also important because there is a Doppler effect. Okay, so all this, therefore, I will be mostly interested in these two quantities, potential and density contrast in baryon photon medium. But potential I didn't derive for you, but let me recall our Einstein's equation for gravitational potential, which tells me that in the subhorizon regime, let me just come back to it. Here it is. This one, I'm in the ideal fluid approximation, so psi is phi. These terms are irrelevant in subhorizon regime. This one is relevant. So the potential, gravitational potential, which at that time is dominated by dark matter component, so let me call it dark matter, it's given by 4 pi g a squared delta rho dark matter over k squared, right? We have figured out that at matter domination, and recombination occurs at matter domination, this guy grows with a scale factor. Sorry, the density contrast. So delta rho dark matter is delta dark matter times rho dark matter. Okay, this delta dark matter goes like A, rho goes like 1 over A cube, and I have here A squared. So the potential stays constant, as we figured out in the last lecture. The potential for dark matter particles is constant at matter-dominated epoch, independent of time. But what's important here is 1 over k squared dependence. Okay, so all in all, this is equal to some numerical factor, which turns out to be rather large, times the initial value, zeta, times 1 over k eta equality squared. And remember, there was also logarithm, times logarithm of k at equality. Okay? So doesn't that make sense to you? I think it should. Right? There is this logarithmic enhancement of logarithmic factor, which we basically derived. This one, 1 over k squared, turns out to be rather important. This gravitational potential decreases as momentum increases. Shorter wavelength has smaller amplitude of the potential. So let me continue with delta. It has a part which is proportional to the dark matter potential. Why? Clear, because once you have gravitational wells, then there is more matter in these gravitational wells, right? Even though this is relativistic matter, still it's concentrating in gravitational wells, right? So the density contrast in matter, both relativistic and non-relativistic, is positive in gravitational wells, negative on the top of gravitational hill. So there is this number, and it's a good exercise to figure out what this number is. What is this number for photons? Classical statistical mechanics. I mean, what is this number for photons? Or in other words, this is proportional to temperature perturbation, right? Delta B gamma, delta rho B gamma over, say for photons, delta rho gamma divided by, suppose that there are no baryons. Then this is 4 times delta T over T, right? The higher the density of photons, the higher the temperature, and vice versa. Right? Rho is Stefan Boltzmann, 2 times pi squared over 30 T to the 4th. Right? For photons. Forget about baryons. So what is delta T over T in a potential well? Assuming that the potential well is small. What is this number? Hey, gentlemen, ladies, what is this number? Okay, this is homework for you. I thought everybody would know. Okay, I will not give you a hint. If I give you a hint, you will immediately jump and say, ah, this is the number. No. Okay, so anyhow, there must be, once you have gravitational potential, in this case produced by dark matter, then there is, for pure photons, this is pure photons. For pure photons, there is a well-defined relation here, which gives you the, which on general grounds you should grasp, you should guess immediately what it is, but okay. If you have baryons, this number is different. And that's important. That's very important for understanding how does the cosmic microwave background know about the baryon fraction. Why is it so precise in measuring the baryon fraction? Okay, this is a homework. So What is this number for photons, pure photon medium? And what is this number here if there are not only photons but also baryons? It should be possible to express this in terms of baryon energy density divided by photon energy density. Baryon to photon fraction of energy densities. Huh? Which one? No. No, of course not. I mean, it's gravity. You have a gravitational well. If photon comes into this gravitational well, it becomes red. Blue. Its temperature increases. So in the potential well, photon is. I'm giving you a hint. Come on. Anyhow. Oh, no, it's not zero. All right. So that's what the story is. You have gravitational potential here, and you also have variations over space of temperature, or in other words, energy density of baryons and photons, okay, which is dominated by photons. Okay, so what we actually need is the gamma, the photons themselves. It's not baryons but photons in the situation where we have both baryons and photons in the medium. Okay, because this is proportional. This relation here is valid for photons, so I need this for photons. So that's my summary of perturbation as recombination. It's basically, I cannot treat the intermediate scales, the intermediate scales of momenta in between the scale 1 over eta recombination and 1 over eta equilibrium. So I cannot treat the angular scales between 1 over 50 to 1 over 150. That's analytically is very difficult to treat. But otherwise, that's the overall picture. Now, let me, let me still, well, shall I finish or can I continue for another 5 minutes? Okay, let's maybe continue, because that will leave me time for discussing CMB from the very beginning of the next lecture. So I mentioned baryon acoustic oscillations. Where do they? What is this? Well, let's come back to this formula here, right? The density contrast in baryon photon component, which is tightly coupled at not very high momenta. This is a tightly coupled system due to photon interactions with electrons and Coulomb interactions of electrons with protons. All these species travel together, okay, make one and the same medium. And by recombination, it has this behavior, cosine sound horizon at recombination times k. Okay? Oscillatory behavior as function of momentum. Now, after recombination, assuming that recombination is very fast, which is true for wavelengths I'm discussing, this oscillatory behavior freezes out for baryons. Now, okay? For baryons, it freezes out because immediately after recombinations, baryons are in atoms. Atoms do not interact with photons. So we have non-relativistic baryon medium, atoms, gas, and the gas is so dilute that pressure in this gas is negligible. The velocity of sound in this gas is completely negligible. There are about 250 atoms per cubic centimeter at that time. I mean, what is the sound speed in this medium, right? 0. Okay, so by the time of combination with density contrast oscillating as function of momentum, so does this oscillatory behavior persists in the baryon component, okay? Now, after recombination, baryon component is a part of dark matter component, of matter component, non-relativistic matter component. In the end, they grow together, as we discussed yesterday. So the matter density contrast has a smooth piece that we discussed yesterday, which grows like everything grows like scale factor, but there is a smooth piece, and there is this oscillatory piece plus for zeta. But now you have to understand that this is only in baryons, not in dark matter. So, and delta m is the ratio between density contrast in all matter particles divided by total matter energy density. So this is d omega cdm plus omega baryons times cosine rs times k. Okay. So in the power spectrum, and this smooth part, since we only have one initial condition, it's also proportional to zeta. So if you do the correlation function, this is a small number, this ratio. This one is a lot bigger. So the correlation function, in other words, P of k, will have P matter now. We'll have a smooth part and oscillatory part, which is suppressed by this ratio here, and in fact there is also numerical suppression times numerical factor times cosine rs times k. All right, and these are called the baryon acoustic oscillations. You have oscillatory behavior of the power spectrum as function of momentum. Okay, this is seen in the galaxy distribution functions. So this is power spectrum inferred from galaxy distribution functions. These are all data, but they illustrate the point very well. So there is an oscillatory pattern in the power spectrum. This is essentially power spectrum normalized to the smooth part. You see the effect is at the level of a few %, but it's there. There are not very many oscillations. Short wavelengths are different. They get smeared out for all kinds of dissipative phenomena, but few first oscillations are visible. How can you interpret that? Interpretation is actually quite simple. Interpretation is this. You consider the as an example, suppose that there is an initially overdense region, okay, in the universe, where there were, since we have adiabatic mode, everything was more abundant here, both photons and baryons and dark matter particles. Temperature was higher here. Okay, so this is overdense region. While it is larger than the horizon size, nothing happens. Right? It stays there. In superhorizon region, nothing changes. But once you get into the horizon, things start to develop. Dark matter will stay right? It's pressureless. It doesn't move anywhere. But photons and baryons, okay, you have overdense region. What if you make an overdense region here? What's going to happen? There will be a spherical wave going out, right? So photons and baryons, in particular baryons, will make a spherical wave away from this overdense region. So there will be an overdense region now in here, okay? This means that there is a correlation between point here and region there. So you expect additional correlation at what distance? Well, all this wave proceeds until recombination. Once recombination occurred, it stops, baryons stop. So you expect the correlation function between, say, delta meta of x, y in coordinate space be enhanced when the distance between x and y, coordinate distance, equals to the sound horizon, coordinate sound horizon of recombination, right? Because the coordinate distance this wave travels is just the sound horizon by definition, right? The distance that signal travels from essentially 0 time to given time, which is recombination, okay? So you expect in the coordinate representation, you expect some bump in the correlation function, which is there. That's, here it is. It's a galaxy-galaxy correlation function from SDSS survey. This is separation. This is the bump. Okay, here it is. That's again old data. There are a lot more now, but that's again nice illustration of what's going on. You have a bump in the correlation function in the baryon plus dark matter. In the galaxy-galaxy correlation function, you see the bump. And if you make a Fourier transformation of this bump, you get oscillatory Fourier transform. That's how you interpret baryon acoustic oscillations. Why is it important? Well, first of all, it's a nice, it's nice to check that we understand what's going on in the universe. And second, which is more important, is that we have a standard ruler, right? Because this horizon size, the acoustic horizon size, is very well calculable, since you know the recombination temperature, you know how the universe evolves before the recombination, and once you know the dark matter content, then you know the time that passed from the beginning, from the Big Bang to recombination, and you know the sound horizon at recombination. So the sound horizon at recombination is a ruler. Of course, it gets redshifted, but we know how it gets redshifted, right? So it's a standard ruler at different redshifts, and having a standard ruler or standard candle in the universe is very useful, because then you can, measuring angle at which you see the standard ruler given z, you know what is the distance to the sources at given z, at given redshift. So there is distance redshift relation inferred from observation of baryon acoustic oscillations, which is very nice. And since it's so robust, there is not so much uncertainty in there. our experimental colleagues eagerly include this data in their analysis. We have a standard ruler, which is baryon acoustic oscillations, and physics is pretty simple. It's just acoustic waves in the acoustic standing waves in the universe before recombination. That's it.
Are there some urgent questions or not so urgent? Besides jokes, if you have questions, we have 5 minutes.
Okay, you talked about the non-Gaussianities and that a free field has a Gaussian correlator only in vacuum. Because I know that there are proposals of taking a non-standard vacuum in inflation and generating non-Gaussianities through this.
Yeah, there are proposals of this sort, but
they are okay.
Yeah, but you know, it's not there are many proposals on how non-Gaussianities can arise. Non-Gaussianity is a big issue, both theoretically and observationally. But unfortunately, and I will give examples of how simple non-Gaussianities could be generated in my lectures on inflation. But today, there is no signal yet. And in fact, the limits are pretty strong. They're kind of disappointing. They're maybe too strong for exotic but relatively simple models to be rolled out. Other questions?